Okay, so last time we were looking at the assumptions of the kinetic model, and in the assumptions we had understood that the molecules occupy very little space and there is no intermolecular attractive force. And one of the important assumptions was that all collisions are perfectly elastic. So we're going to make use of this particular concept here, that all collisions that occur, whether it is collisions between molecules of the ideal gas, or it is the collision between the molecule of an ideal gas with respect to or colliding with the inner surface of the container, all such collisions are perfectly elastic. That means there is zero loss of kinetic energy. And we had also seen that the molecules move in perfectly random Brownian motion. So the particular name given to the type of perfectly random motion was Brownian motion. So about Brownian motion, what we had learned last time is that because the velocity of molecules is uniformly distributed, or the probabilistic distribution of velocity is equal for all directions, therefore RMS speed, which is square root of average of v square, which is square root of summation v square over the number of molecules divided by the total number of molecules. This quantity, so this VRMS becomes 3 times square root of Vx square's average, because V square's average is Vx square's average plus Vy square's average plus Vz square's average, because the molecules velocities have 3 mutually perpendicular components, Vx, Vy and Vz. And because of the random nature, the perfectly random nature, and therefore the equal distribution of velocity over all 3 directions, x, y and z, we have Vx square's average is equal to Vy square's average is equal to Vz square's average. So from this principle we get this over here, or we can also express it as the square of the RMS speed is equal to Vx square's average 3 times, which is the same thing as Vy square's average 3 times, or 3 times Vz square's average. Okay. So these are some of the things that we had looked at in the last lecture. So this was an important result for us, which we'll be carrying forward today in our further derivation from the kinetic theory or the kinetic model of ideal gas. So please let me know if there's any doubt about this particular step over here. Okay, now taking this further, yes. So basically, see, Kunja and Hitanshu, for both of you, I'll just answer the question commonly. If a particular particle, okay, if the ith molecule has a velocity vector which is given by some x component added with some y component added with some z component, okay, then the magnitude of that ith particle's velocity is square root of vx square plus vy square plus vz square. Okay, so in our container, gas molecules have velocities which are randomly distributed in terms of direction. So what that means is that if we randomly pick out one molecule is equally likely to have a velocity direction in any particular direction. It's equally likely to be moving along the x-axis as it is likely to be moving along the y-axis or z-axis or xy plane, any angle, and so on and so forth. Okay. So suppose a particular molecule has a velocity like this, the magnitude of its velocity is this. So then the RMS or root mean square of speed is given by this calculation that we take square root of the mean of the square. Okay, so we have to calculate the mean of v square over the entire sample of molecules and then take its square root. Okay, so what we had understood, for example, if I have some quantity n, where n1 is some value, let's say -1, n2 is 0, let's say n3 is +2, n4 is -2, and so on and so forth. Then how do we calculate the RMS value of n? We calculate it by taking square root of mean of square. So that is square root of n1 square plus n2 square plus going up to whatever last term is there, divided by the number of terms. Okay. So this would become square root of -1 square plus 0 square plus so on and so forth, going up to the last term, dividing by the number of terms. So this is the concept of calculating RMS, root mean square. Okay. So going back to RMS speed or RMS velocity, this term, it becomes summation of vi square divided by the number of terms. Okay. So basically this becomes square root of summation of vx square plus vy square plus vz square for all the molecules. Okay. So up to this term, it is just a definition of RMS. Okay. Now, Hidanshu, to answer your question, how does the last step come? Now, because the motion is Brownian, random motion. Okay. So Brownian random motion means that the direction of velocities has equal probability in all possible directions. So because of this factor, okay, Vx square's summation divided by n will be the same thing as Vy square's summation divided by n, will be the same thing as Vz square's summation divided by n. Because no one particular axis is favored over the other, or no one particular direction is favored over the other. So that is why we can say that Vx square's average is the same thing as Vy square's average is the same thing as Vz square's average. Okay. So in other words, we can therefore say that Vx square's average plus Vy square's average plus Vz square's average, that is nothing but 3 times Vx square's average, because these are equal. So this relation that we are writing is as a direct consequence of the statement of Brownian motion or the definition of perfectly random motion. So Hitanshu, is this clear now? Okay. And Kunj, your doubt is also clear, Beta? The components of velocities, that thing is clear. Yeah. Okay. So now when we introduce this step over here, you can see that basically what we are saying is that Vrms is square root of Vx square plus Vy square plus Vz square, whole thing's average. So that is nothing but Vx square is average plus Vy square is average plus Vz square is average. So actually we'll substitute this here now in this step. So this becomes, okay, so that's how we get this. Or we can say that Vrms square is 3 times Vx squares average, or 3 times Vy squares average, or 3 times Vz squares average. Okay, so that is how we get this particular very important result. This is an important property of Brownian motion. Perfectly random motion. Okay, so I'm hoping this is clear to all of you. Just take a look at the steps here. We'll continue ahead. Because now we'll be making use of this particular relation that we have between Vx square's average and Vrms square. No, Aditi, you don't need to note this down because it's already done in this step earlier and also in the previous class. So now next thing, we will apply the collision theory, okay, to find out Vrms in terms of pressure, volume, temperature, or state of a gas. So for this, we do a very simple derivation in which we apply the elastic collision concept, perfectly elastic collision concept. So we have a perfectly cubical container, cubical gas container, okay, of dimension L by L by L. So the volume of the gas inside is that. Now inside that, we are having an ideal gas which has all the properties we've discussed earlier in the kinetic model. So this is an ideal gas n moles of an ideal gas at pressure P, okay, volume V equal to LQ, because that's the volume of the container, and temperature, this is absolute temperature in kelvins, that temperature, okay. And also this now has a property that this ideal gas has molar mass capital M. So for example, you know that oxygen, it has molar mass equal to 32 grams, or 32 into 10 raised power minus 3 kilograms. Similarly, if you take hydrogen gas, it has molar mass of 2 grams. If you take helium gas, it has molar mass of 4 grams, etc. like that. So also, it will have, we will denote with a symbol capital N. So that is nothing but number of moles multiplied by Avogadro's number. That is the definition of Avogadro's number. And therefore it has molecular mass, that is mass per molecule, which will denote with the symbol small m, that is molar mass divided by Avogadro's number. Okay. So these are the properties of the ideal gas: the state of the gas, pressure, volume, and temperature, and also the molar mass being capital N. So from that we can designate the molecular mass, that is mass of each molecule small m, as molar mass capital M divided by Avogadro's number. Similarly, if the number of moles is small n, then the number of molecules present is a very large number, because Avogadro's number is very large, 10 raised power 22 order of magnitude. But anyhow, the number of molecules become number of moles multiplied by Avogadro's number. Okay, so now to this gas, we will just apply the properties of an ideal gas according to the kinetic model, and from that we will understand how to relate the RMS velocity. So inside this gas chamber, now let us say we have designated the XYZ coordinate system in this manner, that okay, so this is my XYZ system. Now let's consider this wall. Okay, so this is a wall of area L square. Okay, so the pressure of the gas P, that will be equal to force per unit area that the wall experiences. This will be force due to collisions that the molecules make on the wall. Okay. Due to the collisions on the wall made by the molecules divided by A, which is the area of the wall. So we can relate the pressure with the force per unit area that the molecules apply due to collisions. And we will relate the collision force with the momentum with which the molecules hit. And from that, we will get a relation for the RMS speed. So let's understand it this way. So now suppose on this wall is parallel to the YZ plane, as you can see in my diagram. These two side walls are parallel to the YZ plane, whereas the ceiling and the floor, they are parallel to the XZ plane, right? And the front wall is parallel to the XY plane, like that. So on this wall, which I'm redrawing over here, which is basically parallel to the YZ plane. Okay. Now, if a particular molecule moving at some velocity v and of mass m makes a collision with this wall, so now I'll make a two-dimensional diagram of that collision. So what will be the velocity of the molecule immediately after the impact? That you know from the concept of perfectly elastic collision. If on this wall a molecule moving with velocity like this makes a perfectly elastic collision, what happens immediately after the collision? The molecule goes off like this with some velocity, let's say v prime, like this. So if the impact velocity, that one is vx I cap plus vy j cap plus vz k cap, and as you can see, the wall is parallel to the yz plane. So what will happen is on impact, the wall will apply an impulse, it will apply a collision impulse along the negative x-axis. Okay. So because of that, the velocity after impact, the velocity will become, let's say, v prime, which will be minus vx I cap plus vy j cap plus vz k cap. Why? Because it is a perfectly elastic collision. So in a perfectly elastic collision, the approach velocity must be equal to the separation velocity. Okay. So that is why this becomes minus vx, because coefficient of restitution is equal to 1. So as a result of that, we can see that the impulse due to the collision is nothing but change in momentum. Impulse is equal to change in momentum, so that is m into final velocity minus initial velocity before the impact. When you subtract these two, you can see that the collision impulse is 2m vx. So why this happens, you have to understand, because the wall being parallel to YZ plane, okay, Vy j cap plus Vz k cap, this part is the tangential component. So tangential component of velocity को क्या होता है? It remains unaffected. So this is not affected in the collision. It remains conserved. Whereas Vx I cap जो component था, that is the normal component. That is why we have taken it as the approach velocity. So this component, it gets reversed on impact. So it changes to minus Vx I cap, whereas this remains same. Okay. So that is why the final velocity after impact the tangential component By j cap plus Vz k cap is remained unaffected, whereas the normal component, its reverse direction, it has gone from plus Vx I cap to minus Vx I cap, because um, an impulse of this much, we write it as a vector properly, this impulse you will see is this minus this, so it is minus 2m Vx I cap. This type of impulse is applied by the wall on the molecule. Okay. So this is the collision theory concept that we are applying over here. So this is what is happening on collision of a molecule mass small m with a wall of the container. So the magnitude of that impulse we can just write as 2 MPS. Okay. So just make sure you're clear up to this concept over here. That is the application of collision theory. Then we'll see from this application of collision theory how we will convert impulse into force, and then force into pressure by dividing by area. And from that we will get the relation between RMS speed and pressure. Yes, Ayush, you have to be clear about this derivation. No? So you have to understand this. So the calculation of impulse due to a single collision, where the collision velocity is Vx I cap plus Vy j cap plus Vz k cap. So the impulse due to the collision becomes minus 2m Vx I cap, like this. This part you have to write down and understand clearly. Okay, so now once we understand this equation here, so all of you finished with this. So we can see that on this wall, if a molecule collides like this, then due to the collision, equal and opposite amount of impulse acts on the wall. So that impulse is equal to 2mvx also. Okay, so this is the impulse on the wall from a single collision. Okay, now force is equal to the rate of impulse with respect to time. How we know this? Because force is defined as rate of change of momentum. Okay, and impulse equals to change in momentum. Okay, so therefore average force becomes rate of impulse with respect to time. So this concept that the average force acting equals to the rate of impulse with respect to time. Okay, so now in our container, suppose we had just a single molecule. Okay. So what happened is that that molecule moving with some velocity like this made a collision. So the first collision, suppose that was at some time 0. Okay, so after that it reversed its direction like this. It would have made another collision somewhere, then made another collision, and maybe come back over here like this. Now all the collisions are perfectly elastic. Okay, so what is happening is, because all collisions are perfectly elastic, okay, the magnitude of velocity remains constant. Okay, and this remains constant, or mod of Vx, this remains constant. Why? Because there's no loss of kinetic energy. Perfectly elastic means no loss of kinetic energy. So what will happen is that at the second impact that the same particle makes with this wall only, if the time is delta t, that time will be 2L by Vx mod. Why it will be 2L by Vx mod? Because you can see that if it was moving in this direction with a velocity Vx I cap plus Vy j cap plus Vz k cap. Okay. Now just now it made this impact. Now after the impact, its velocity in this direction is minus Vx I cap plus Vy j cap plus Vz k cap. Then after some time it made a collision here, and then its velocity in this direction, let's say, is V double prime. So that V double prime still has the same x component minus Vx I cap, but it now has some negative y component like this, and then it makes a collision somewhere here. So between the collision here and the next collision on the opposite side, you can see that A to B, the time taken will be the x component of displacement divided by the x component of velocity. So that is L divided by Vx. Okay, and therefore B to A, that is back to A, that time will also take the same delta x by Vx. That will also be L by Vx. Okay, so that is why the total time taken to return back to the original wall, that will be this much. Okay, so that is why delta t, the time between successive collisions, on the same wall. So it's like from that wall to go to the opposite face, it takes a time of L by Vx. And then to come back from that opposite face to this original wall, it takes another time of L by Vx, because the magnitude of x component of velocity is not changing in between. Okay, so that's why this total time delta t will be 2 times L by magnitude of Vx, because the mod of Vx is remaining constant throughout the motion. No matter how many times it collides in between, the mod of Vx is remaining constant. So that is why between two successive collisions with the same wall, the total distance traveled along the x-axis is 2m, and the magnitude of velocity along the x-axis, the magnitude of x component of velocity, that is remaining constant of Vx. So the time taken is 2L by mod of Vx. Okay. So once we have this, now from this we can calculate the impulse next. So just make a quick note of this part also first. Okay, so but a particular impact gives you a collision impulse of this much, and then the time taken from this impact till the next time the same molecule impacts, that time is given by delta t equal to 2L by Vx. Why? Because the component of displacement or the component of motion along the x-axis is traveling a total distance of 2L along the x-axis before it comes back to that same molecule, the same wall. So it's traveled a total distance of 2L along the x-axis at a speed of, or at a magnitude of component of Vx. So the time taken will be the total distance along the x-axis, that is 2L, divided by the component of velocity along the x-axis, that is Vx mod.
Yes, sir.
Yeah, beta?
Done, sir.
Okay, written this down.
Yes, sir.
Okay, so therefore the average force from a single molecule colliding is the impulse divided by the time between two successive collisions. So that is 2mvx divided by 2l by magnitude of vx. So that becomes mvx squared divided by l. So this is the average force due to collisions from a single molecule. Okay, successive collisions from a single molecule. Okay. Now remember that the gas sample in the container, it has capital N molecules, okay, where capital N is number of moles into Avogadro's number. So therefore the net force on the wall, okay, which is due to successive collisions by N molecules, not just a single molecule, but this same thing is happening with N number of other molecules. So that net force will have a magnitude of N times average. So that will become N times mvx squares average divided by L. Okay, because single one give us this much force. Okay, sorry, give us just this much force. So now n different molecules, so they'll have different values of Vx. So the forces will be mvx square for the first one plus mvx square for the second one, like that. So that is the same thing as the number of molecules into Vx squares average. So that is the net force. Okay. So finally, what we had seen is that the pressure acting on the wall. So because of all these collisions happening continuously on the wall, so there are collision impulses which are continuously acting. So that is creating some amount of net force. So that net force is this value. Okay. So the pressure that the gas is applying on the wall, that is the net force because of collisions divided by the area of the wall. So that is n times small m into Vx squares average by L. That is your force divided by area of the wall. You'll remember is L square. Okay. So the pressure becomes total number of molecules into molecular mass into Vx squares average divided by, now this becomes L cube in the denominator. So that is nothing but the total volume of the container or the volume of the gas. So we have this interesting relation that P is equal to Nm Vx squares average divided by volume. Or from this we have that Vx squares average is equal to PV upon Nm. Okay. And now we will use the Brownian motion formula that we had got to convert this relation from Vx squares average to RMS square velocity or RMS speed. So that will be the final step from which we will get the relation between RMS speed and the state of the gas, that is pressure, volume, etc. Okay, so quickly go through these steps. Make sure you understand them. Ask me if there's any doubt. So in the previous part, we saw how we got that delta T to be 2L by mod of Vx. So now we're just using the definition of average force between two successive collisions is the impulse on a single collision divided by the time between two successive collisions. Okay, so once you applied the collision theory concept, it's pretty easy, the rest of the derivation. Okay, so now use the property of Brownian motion. RMS speed was square root of 3 times Vx square's average. This was what we had seen about Brownian motion earlier. That is why I told you that's an important thing, or we can say that V RMS square is 3 times Vx square's average. So from here now, V RMS square is 3 times PV divided by Mn. So we get the relation, which is the most important and significant part of kinetic theory of gases, which is RMS velocity in terms of pressure and volume. This relation, okay. So the derivation is not important from your exam point of view, but you have to understand the logical steps of the derivation so that any conceptual question you can answer about it. Okay? So that is why we have spent some time going through the derivation. So you don't need to, repeat the derivation step by step at an exam level, but you should just be very clear about the logic behind each of the steps. That is important from your understanding of kinetic theory of gases, and from that you'll be able to answer any conceptual questions based on this. Okay. For application, of course, what is the important thing is the formula. Okay. Now in this formula, the very interesting thing is that the denominator n into m is nothing but the total mass. Is any question, people?
नहीं क्या है गलत किए आप गलत किए
Yeah, Itanshu, you have any question, beta?
Such a by mistake.
Okay. Yeah, so this is nothing but total mass of gas. So it is number of molecules, no? It's number of molecules into mass of each molecule. So n into small m is also the same thing as number of moles into molar mass, because of this relation. Okay, so n into m is the same thing as number of moles into molar mass. So we can also write this relation as square root of 3 PV divided by small n into capital N. Okay, so let's look at a quick example. So a container has helium gas at a pressure of 2 atmospheres, volume of 4 liters, and or you can say it has five moles of helium gas at this. So we have to find the root mean square velocity for its molecules. Okay. So it's very simple. This is a formula based question. Vrms will come as square root of 3 PV divided by N into M. Now P, which is 2 atmospheres, we will convert into pascals through this conversion. Okay. So 1 atmosphere is approximately 1.01 into 10 raised power 5 pascals, or that is the same thing as Newton per meter square. Okay. Volume, which is 4 liters, will become 4 into 10 raised power minus 3 in meter cube, because the volume conversion is given by this, that 1 milliliter is the same thing as 1 centimeter cube. So 10 raised power minus 3 liters is the same thing as 10 raised power minus 6 meter cube, or 1 liter is the same thing as 10 raised power minus 3 meter cube. So this is the relationship between liter and meter cube. Okay. And molar mass of helium is 4 grams. So that will be converted to SI unit as this, and N is equal to 5 moles. Just a number. So now this proper SI unit, the values have to be substituted in the proper SI units. Okay. Pressure into volume divided by number of moles into molar mass. So this will give us the velocity in the RMS velocity in meters per second. Okay. So let's just do this calculation. Okay, and this is a typical type of value of RMS speeds of gas molecules. Unless they are at extremely high pressure or extremely high density or something, RMS speeds of gas molecules have an order of magnitude similar to the speed of sound. Speed of sound is 340 meters per second. So most ideal gases at something reasonably close to similar type of state as the normal atmospheric temperature pressure kind of state, they will have RMS speeds which are of the range of few hundred meters per second. But like I said, when doing the numerical calculation, we have to be very careful about substituting the units properly. Okay, so hope you are clear about this and written this down. If any doubt, please ask me about the substitution and the calculation finally. So this one is the first important formula for us from this whole series of derivations. This formula has come with the application of the perfectly elastic collision concept and also with the Brownian motion concept, both the things combined. Hence, it was important to understand those assumptions about the kinetic model of an ideal gas. So in JEE, you will not be asked directly about the assumptions of the kinetic model or any theoretical questions like that. The questions will be numerical, but you can be asked a conceptual question about the relationship between RMS velocity and pressure, volume, etc. So for that, you should understand the derivation process. Okay, that's why we've done the derivation. Once you understood the derivation, it's really the formula which is more important. Okay. Now coming to the next thing, part of kinetic theory of gases is the kinetic interpretation of temperature. So this means that how do we interpret the physical quantity of temperature on the basis of the kinetic model or on the basis of the fact that gas molecules are moving. A bit of pressure into volume, now you have to substitute the product, but in SI unit. Okay. So in this formula, na, that Vrms is equal to square root of 3 PV by Nm. If we want the velocity in meters per second, which is the SI unit, then everything else should also be in meters per second in SI unit. So pressure should be substituted in pascals, volume should be substituted in meter cube, and molar mass should be substituted in kg, which are the SI units. We cannot use hybrid units. Okay, so atmosphere is not the SI unit. Pascal is the SI unit. So the relationship is 1 atmosphere of pressure, or what is also called 1 bar pressure. In the language of barometry, it is called 1 bar. That is equivalent to 1.01 into 10 raised power 5 pascals. Okay. Similarly, 1 liter of volume is equivalent to 1,000th of a meter cube. Okay, that I explained above also. So hope this point is clear now.
Yes, sir.
Okay, Vita. Yeah, now coming back to kinetic interpretation of temperature. So that is on the basis of kinetic theory, which is about motion of gas molecules. How do we interpret the physical property or the physical quantity of temperature? So that is this way, that the absolute temperature of a gas, capital T, that is temperature in kelvins, is what we mean by absolute temperature. Temperature in absolute scale or Kelvin scale. It is a quantity which is directly proportional to the average kinetic energy of gas molecules. This is what is the meaning of temperature according to the kinetic model. That temperature is a physical quantity which is directly proportional to half m v Rms square. Okay. Because average kinetic energy is half mv squares average. Okay. And Vrms is nothing but square root of v squares average. So v squares average becomes, sorry, not v2, but v squares average value becomes therefore Vrms square. So average kinetic energy of gas molecules, that thing is nothing but half m Vrms square. Okay, because of this relation. So that's how we get this over here. So temperature is directly proportional to this. Okay. Just make a note of this. We'll take it forward from there. Okay, now put this together with what we have learned above. So therefore, temperature is directly proportional to square root of 3 PV divided by capital N into small n square. So temperature is directly proportional to, so we can say that temperature is directly, sorry, capital N in the denominator, not, okay, PV upon small n, because here 3 by 2 is just a pure number, it is dimensionless, so it's a numerical constant, so it does not affect the proportionality, and number of molecules is again number of moles into Avogadro's number. Okay. So proportionality wise it is this way. So this equation is then expressed as this, which you know as the universal gas equation or the ideal gas equation.
Yes, sir.
What we also call the equation of state. So यहाँ पे जो capital R है, that is only the constant of proportionality, and because it's the same for all gases and it's independent of anything else, so it's a universal constant. So that is why we call this the universal gas constant, because it's not affected by anything else. We look at a gas at pressure P, volume V, and temperature T, number of moles N. The relationship between these three quantities is independent of anything else. We might be carrying out the experiment at any part of the world or even outside Earth, okay, and it might be any gas ranging from noble gases to the heaviest of polyatomic gases. Still, the relationship between them will be the same. So that is why the capital R quantity is called the universal gas constant, because it's universal. It applies to all ideal gases in all situations, independent of anything else. Okay. And also from experiment, the value of R comes out to be, as you know, 8.314 joules per mole Kelvin. Okay. So let's also explain how the unit comes out. So this is the theoretical derivation of the ideal gas equation, which comes directly from the kinetic model of ideal gas. From kinetic interpretation of temperature, which is part of it, and the collision theory and all that applied, which we've seen earlier. So otherwise, we know ideal gas equation as a consequence of Boyle's law and Charles' law, which are experimental laws. But this is the proper way to derive it theoretically. And Boyle's law and Charles' law are the experimental laws which verify ideal gas law or ideal gas equation in an experimental point of view. Right, all of you know Boyle's and Charles' law, no?
Yes, sir.
Yeah. So those are experimentally observed, okay, but they can be justified from ideal gas equation. And ideal gas equation is coming from the this thing, from the kinetic model, as you can see. Okay, very good. Okay. So just to understand the units over here in this equation, P into V, its unit is Pascal into meter cube. So Pascal is the same thing as Newton per meter square. So that is Newton meter or joule. Okay. So therefore, pressure into volume has the dimension of energy. Okay. And therefore has the unit of joules. Okay. So that's why the dimension of R being PV divided by temperature into number of moles. So it is R is expressed in joules per mole Kelvin. SI unit of R becomes like this. And in physics, we will always do calculations using ideal gas equation using the SI unit system. So we'll always take the value of R in joules per mole Kelvin rather than liter atmosphere per degree C. And there's also the alternate unit of R in liter atmosphere per degree C, per mole degree C. But we won't be using that. We'll be using this. Okay. So now once we have got this thing, the ideal gas equation and kinetic interpretation of temperature. So let me list out the formula we have got so far. Vrms we saw was square root of 3 PV divided by the total mass of the gas sample, which we can also write as number of moles into molar mass. Okay. Then we saw that temperature is directly proportional to half mvrms square. So combining this and this, we saw temperature is directly proportional to PV upon capital N or PV upon small n. So from this we got the ideal gas equation. Okay. Now also this can be written as PV is equal to capital N into something called Boltzmann's constant. Might have heard this term Boltzmann constant in chemistry. Small k, this is called Boltzmann's constant. Okay. And it's very simple. Boltzmann constant is nothing but universal gas constant divided by Avogadro's number. So you can see here that N into R is the same thing as capital N upon Avogadro's number into R. That's how it becomes N into K, because K is R upon Avogadro's number. So there's another way of expressing the ideal gas equation. One way is in terms of the number of moles and the other way is in terms of the number of molecules. So always our notation is the same. Capital N stands for number of molecules, small n stands for number of moles. Okay. Now having got this, the next thing is that RMS speed can also be expressed in terms of by using PV equal to nRT. It becomes this or this. Okay, because PV upon NM is equal to or PV upon number of moles into molar mass is nRT upon. Okay, so this equation gives us this. Okay. This equation gives us this, but this is the relation between RMS velocity and absolute temperature.
Done, sir.
Yeah, beta. Written down.
Yes, sir.
Okay.
Yes, sir.
Yeah. So now let's look at another example. We have two different containers, okay, A and B, which contain some ideal gas. Okay. So container A has oxygen gas, okay, at a pressure of 2 atmospheres, volume of 2 liters, and a temperature of 300 Kelvin. B has helium gas at a pressure again of 2 atmospheres, but the volume of the container is less. It is 1 liter. Okay. And the temperature of the container is, temperature of gas in the container is 400 Kelvin. Assume they are insulated, okay, containers. So there's no heat escape from inside the container to outside, or vice versa. So now we have to compare the two. So we have to find first the ratio of number of moles, okay, in A and B. Number of moles of gas in A and B. Okay. Then we have to find the ratio of RMS speed of oxygen and uh, helium molecules. That is VRMS in A is to VRMS in B. Okay. And we also have to find out the ratio of average translational kinetic energies. This quantity in A is to B. What is the average translational kinetic energy of the oxygen molecules is to the average translational kinetic energy of the helium molecules. Okay, very simple question, but it's about interpretation. So just try to work this out quickly and make sure you get this correct. Okay, so let's see what answers people have got. So Kunj, you have sent me some answers. Rusker, ratio of number of moles. Okay. Okay, so let's see. So all we have to do is, for the first part, we will use PA VA upon TA and PV VB upon TB is proportional to NB. So ratio of number of moles will just become ratio of pressures into ratio of volumes into inverse ratio of temperatures. ऐसा हो जाएगा. So Na by Nb will become 1 into half, sorry, into 2. Volume of A is double of volume of A, B, into ratio of temperatures का inverse, that is 4 by 3. So 8 is to 3. That is the correct answer. Some of you have sent me that answer. So ratio of number of moles in the first container to number of moles in the second container, or number of moles of oxygen is to number of moles of helium, because those are the gases given. That is 8 is to 3, right? Yes, very good, Ruksar. Your next answer is also correct. Okay. Now for the second one, RMS speed, we'll just use the formula. Now see, since you already know the ratio of number of moles, we can just use that only now. Square root of 3 RT divided by M. Okay, so VA by VB will become square root of TA by TB into molar mass in B divided by molar mass in A. So 300 by 400. A molar mass of helium is 4 grams. Molar mass of oxygen is 32 grams. So this will become square root of 3 is to 32. So this is the easier way of calculating this. We can also use the square root of 3 PV by NM formula, and we can incorporate this in that. Remember that M is molecular or rather molar mass. So M in A is the molar mass of oxygen gas. So that is 32 grams.
32.
Yeah, don't make the mistake of 16 grams. That is atomic mass. This is molar mass of O2. Whereas helium is monoatomic, so it is just
4.
right. Okay, so Kunj, you understood now, beta. The probably made some calculation mistake or something, but okay. We can also use this, that Vrms is square root of 3 PV divided by Nm. So Va is to Vb, Pa by Pv, Va by Vb into Nb Mb divided by Na. So this should give us the same thing. So pressures were same, volume ratio is 2:1, number of moles in B is 3:8 compared to A, and this is again 4 by 32. So as you can see, this will also give you the same thing. Okay. But obviously you use whichever seems more convenient and faster. Now let's come to the third part, the average kinetic energy. So that is the average translational kinetic energy. Now this is the easiest thing. This you should just remember that half m Vrms square is directly proportional to temperature. Okay. So the ratio of these two will be nothing but the ratio of the temperature. So it will be 3:4.
Yes, sir.
Yeah. So this was very good. So this was the part which was oral for the question. Chamber E is to nothing but okay. So this is one type of calculation or application you have to be very good at doing with kinetic theory of gases. Okay. And you should not mix up the formulae so that you know that which quantity depends on which is independent of temperature, which is independent of number of moles, etc. All right, now next let's look at slightly more complex type of application of equation of state. Okay. So next example. Now suppose we have a closed chamber which has oxygen gas at pressure of 3 atmospheres. Total volume of the chamber is 5 liters and at a temperature of 127 degrees. Okay. And this is not only closed, but it is also insulated chamber. It's heat insulated. It's double walled and heat insulated. Now outside, the atmospheric conditions like this, atmospheric pressure is obviously 1 atmosphere. Temperature is 27 degrees. Okay. Now a small orifice. Orifice means a very small opening, aperture or opening. Is opened and oxygen leaks out till the pressure stabilizes. So first of all, we have to find the final state, that is pressure, volume, temperature of oxygen in the chamber. Okay. Now this is assuming only oxygen leaks out. Okay. Air does not enter. So we got some means by which atmospheric air gases don't enter the room, only oxygen leaks out. And secondly, the total mass of oxygen that leaks out. Okay. So this is also a very simple question, just based on the application of um, equation of state or ideal gas equation, PV equal to nRT. So that's a hint to you. Just try this out. Okay, so anybody solved this? Yeah, I just got one message. Let me check. Yes, very good, Kunj. That's correct. No, so Kunj, one thing you have to understand, the volume of the container remains fixed. So the amount of oxygen in the container in terms of volume of oxygen will remain conserved. Okay, so inside the container, the final volume of oxygen is still going to be the same, 5 liters, same as the initial volume. But that volume of oxygen will be at a lower density because both the pressure and temperature have changed. So a lesser mass, a lesser number of moles, a lesser density of oxygen, all three things are changing, but that is going to occupy the same amount of volume, which is the volume of the container, which is 5 liters. Is the point clear, Kunj? Okay, so compared to this now, when we have opened the small orifice, okay, but it is somehow we have managed what is called a one-way valve. It allows gas to pass only from one direction to another. So with this open valve, what is happening? The oxygen gas inside, it will exist at a pressure equal to the external pressure. It will exist at a temperature equal to the external temperature, but the volume will remain the same, which is 5 liters. So more importantly, if this had n moles, okay, then on opening, this has now got n minus delta m, or let's say n prime number of moles left, because delta n moles have leaked out. Okay, so this is the concept we have to apply. Whereas this temperature was initially 400 Kelvin. Yeah, so anybody got the final answer? Kunj? What is the final answer for mass of oxygen that is leaked out? This total, the second part is answer. So final state to aa gaya apne paas. The final state of oxygen will be at a pressure of 1 atmosphere. Volume remains the same, 5 liters. The temperature becomes the atmospheric temperature outside 300 Kelvin. Okay. So now to get the mass of oxygen that is leaked out, you have to understand that T1V1 was equal to nRT1. Okay. So this N was equal to this thing. Okay. So that was 2 atmospheres. Okay, into 5 liters. Divided by 400 Kelvin. So this was the number of moles. Okay. Now finally in this one, P naught V naught is equal to N prime RT naught, where N prime is equal to N minus delta M. Okay. So this N prime is equal to this much. So it is this much. Okay. So now compare this equation. So that will tell you the number of moles which have leaked out. So N minus N prime delta N. This is number of moles leaked out. Okay. The volume is common, so we'll just write this. So this delta N will be equal to that common volume divided by R into T1 by T1 minus T2 by T2. Okay. So that is 2 by 4 minus 1 by 3. This is the number of moles which have leaked out. Okay, so we can quite easily do this calculation. So half minus 1 by 3 will give us 1 by 6 into 10 raised power. Sorry, first we also have a 1.01. Okay, then into 10 raised power 3 minus 3, so that's 10 raised power 0. So this is the number of moles which have leaked out. So let's do a rough calculation of this. It's almost like 1/10 of a mole. It's approximately 0.01. Sorry, 0.1. Okay. Therefore, mass of oxygen leaked out. That means number of moles into molar mass. So 3.2 grams. So about 3.2 grams of oxygen have leaked out of the chamber. Yeah, after kinetic theory of gases, we'll come to first law of thermodynamics, Siddhanshu. But few things still remaining in kinetic theory of gases, which we'll be discussing. Okay. So one final thing we'll discuss today is that the relationship of average translational kinetic energy. So we already saw that RMS speed was also expressed like this, or another way of expressing the same thing was in terms of molar mass. So this became 3 RT by capital M. Okay. So from this we can see that the average translational kinetic energy per molecule becomes this. So this is also very important equation for us. The average translational kinetic energy per molecule is given by the formula 3 by 2 kT. Okay, thank you. Okay. And additionally, okay, so from this we get this. So these quantities here, they are called the average kinetic energy per molecule per degree of freedom. Because the translational velocity has three components which are mutually perpendicular, or what we call 3 degrees of freedom. So those 3 components are called 3 degrees of freedom in the language of kinetic theory of gases. So the average kinetic energy per molecule per degree of freedom is given by the expression 1 by 2 kT, where K, remember, is Boltzmann constant. Just as similar. Okay, so people, with this we will conclude today's lecture, and next session we will discuss from this point onwards. So this is in itself a very important concept, that the average kinetic energy per molecule per degree of freedom is 1 by 2 kT. We will see that from this we will develop the concept of internal energy of an ideal gas. Internal energy being an important parameter in our first law of thermodynamics principle. So all these things you've seen in chemistry also, so you're kind of familiar with it, but we'll discuss more about it.
Bye, sir. Thank you, sir.
Okay, people, all the best. That's it for today's lecture. Bye.